Jesse.
Great, thank you. Let me just share my screen here. There we go. So let me begin by reminding you about bi-exactness, which I introduced in my last lecture. So first of all, we have gamma, a discrete group. And we have, we have its L infinity algebra, and inside of that L infinity algebra, we have this algebra, let me call it A. So this is the set of functions in L infinity of gamma, such that if you take the function and then you shift by, if you act on the function by the right, so I'll denote that by R sub t. So that's the induced action on L infinity coming from the right multiplication of gamma. So you want that the difference be a C0 function, and this is for all t. So this is some C-star algebra, and we saw last time, so it contains the compacts, which gives you a copy of gamma inside of this. And so whatever, if we look at the spectrum, it's going to be of the form gamma union, and then what we called this boundary of gamma. So this is A. And of course, since we just take the difference with right translation, the group gamma acts on this C-star algebra on the induced action from left multiplication. So this is an abelian C-star algebra. And then we said that the definition was that gamma is bi-exact if the action of gamma acting on either this compactification, or you can just look at the boundary, it doesn't matter, it's the same, is amenable. In the sense that there existed this, so i.e., well, I won't write out the definition again because I won't need it. But this is equivalent, and this is how I'll use it today. I mentioned this last time. This is equivalent to saying that if you take this A crossed gamma, this is nuclear, or equivalently that the bidual of this C-star algebra is injective as a von Neumann algebra. All right, and then I mentioned this theorem of Ozawa at the end of my lectures, last lecture. So that is, this is from, I believe, 2004, maybe 2003, I'm not exactly sure. But that is that if you have a bi-exact group, then it's solid. So if gamma bi-exact, and if you take any diffuse von Neumann algebra, so diffuse, that means there are no minimal projections. So like for a measure space, there are no atoms. The atoms correspond to minimal projections. So if you have a diffuse subalgebra, so then the relative commutant is injective, or is. In particular, if gamma is bi-exact and non-amenable, then L gamma is prime, for instance. So this gives another way of showing Liming-Guz result that, so for example, since we saw that free groups are bi-exact, so you get that L F2 is solid and hence prime. Hence prime. Prime means that it can't be written as a tensor product of any two finite von Neumann, diffuse von Neumann algebras. All right, so let me give you a sketch. So here's a proof sketch. So this is not due to Ozawa. This isn't Ozawa's proof, but this is a proof due to Boutonnet and Carderi. So, and here is the idea. So we'll view, remember, so this C star algebra, this sits inside of L infinity of gamma. And so we can view this cross product here. So we have that this A cross gamma, we can view this as a C star subalgebra of L infinity of gamma cross gamma, which is naturally isomorphic to B of L2 of gamma. So we'll think of everything here as sitting inside of B of L2 of gamma. And now what can we do? Well, we have that since B is diffuse, so since B is diffuse, we can take a sequence of unitaries such that they converge to zero in the weak operator topology. So this is something we already saw when we discussed property gamma. We had some sequence converge to the weak operator topology. And if you remember there, the way Efros showed that property gamma implies interamenability is you took such an asymptotically central sequence, and then you took these corresponding states to it. And we're going to do exactly the same thing here. So we're going to consider the state, or I should say a state on B of L2 of gamma that is a weak star accumulation point of the sequence of states, which is given by an operator T, gets mapped to these vector states, T, UN hat, UN hat. So here I'm identifying B of L2 of gamma with L2 of L gamma, which we already mentioned before. So I can view these things in L gamma as sitting inside of little L2 of gamma. Yeah, so we take some state, which is an accumulation, which is exactly what we did with the Efros thing. And then just as we did before, we note that phi restricted to L gamma gives us the canonical trace on L gamma. So this is the trace we're interested in. We already saw this before with Efros's proof. And we also, if we restrict to the commutant, so L gamma op or the right regular representation, this also gives us the canonical trace there. So we're good with that. And then now the next thing to notice is that the other thing we notice is that since we have that this sequence of UNs converge to zero in the weak operator topology, that means if we put any compact operator here for T, then of course we're conjugating by a compact operator by the sequence which converges weakly to zero. Compact operators, they take the weak topology to the strong topology or the norm topology so that this will converge to zero. So the other thing we need to note is that also phi restricted to the compact operators is identically zero, which is also something we noted in Efros's proof. All right, so now I've had a request that I try to copy over the right-hand side when I move to a new page. So I'll try to remember to do that. I know it's a pain. It's like the worst part of slides is that when you move to a new page, the slide is lost. But I still think it's, yeah. I still prefer chalkboard even in this virtual format to slides myself. Okay, so this is the situation we have here. And now the other thing to notice is that so we remarked here that if you restrict to the compact operators, then this is the case. But also notice that the property of this C star algebra A was that if we take a function and then multiply it on the right, then the difference is compact. So the state can't see the difference in there, right? So note that if F is in the C star algebra A, which was this continuous functions on the group union this Ozawa boundary. And if T is in gamma, so then we have that phi of F minus, not lambda, but rho, because we're conjugating by the right, rho T F rho T star, that this is equal to 0 because it's a compact operator. Moreover, if we multiply this operator, so if we multiply it by rho T on the right, then we see that also phi of F rho T minus rho T F is equal to 0 because, again, this is a compact operator. And now the thing to notice is also if we multiply F on the right by lambda T, then this is true. You get a compact operator. And so in fact, we can look at anything in the C-star algebra generated by this C-star algebra here together with the left regular representation. So in fact, we get that phi of X rho T minus rho Tx is equal to 0. And this is for all X in this cross product here. Cross gamma, where this is conjugation on the left, and this, we remember, we think of all this as sitting inside of B of L2, which is where our state lives. So now, what does this mean? Well, now you can also take spans in rho T, and so you get, again, therefore, we get that now phi of the commutator of X and Y is equal to 0, and this is for X in this cross product. And now Y, anything in the C-star algebra generated by the right regular representation. So the C-star algebra generated by this. And now here comes the kind of the little bit of magic, and that will again use this observation of Kahn that since we have a state here, we can use the Cauchy-Schwarz inequality. And we'll use the fact that the state restricts to the trace on L gamma and also L gamma op, which is where the right regular representation is. Right, so note that here, this is the commutator. So we have the phi of xy minus phi of x y naught, and absolute value is going to be less than or equal to the norm of x times the norm 2 of y minus y naught, and this is for y and y naught in the right von Neumann algebra, L gamma op. That's because it restricts to the trace here. So now if we look at the commutator, and similarly if you put y on the left. So this means in this formula here, which is true for the C-star algebra, we can actually pass to the strong operator topology closure of the C-star algebra and get it for the von Neumann algebra. So therefore, we get that in fact, the state, whenever you apply it to any commutator, this is equal to 0, and this is for all x in the C-star algebra. And for y now in the von Neumann algebra, R gamma. So now again, let me move on to the next page. All right, so now in particular, what we can do is now if we take x, which is in B prime intersect L gamma, hold on one moment. wondering if I switched my right and left here. No, it seems okay. All right. So now what can we do here? Now I want to look at yeah, so now I want to look at, so now we'll take X, and that's right. Okay, so take X in here, and now let's take, I think maybe I changed notation because I was using X there. So let me change this to an A, take A in here, and now take X in this C-star algebra. And now I want to look at what phi of A times X is. Okay, so this looks good. So again, I'll use, so I'm taking A in here, and remember, so we can approximate A. So now I'm going to take AN in the reduced group C-star algebra, such that the norm 2 of AN minus A goes to 0. And so now, again, because the state phi restricts to the trace on the group von Neumann algebra, we can say that this, whatever it is the limit as n goes to infinity of phi of AN times X. And now we're in the, now AN's in the reduced group C-star algebra and X is in this cross product. So now what I can do is now I'll write out the definition of phi. So remember, phi was by definition some accumulation point, or we can approximate it by something of the form these vector states. So AN, X, and now we had UN hat, or K. Right, so this was the definition of phi. But now what can I do? Well, I can take this AN, I can move it to the other side, and then I can use the fact that it commutes with the UKs, because remember the UKs were in B and A is in the commutant of B. So I can rewrite this as, again, we have a limit as n goes to infinity, a limit as k goes to infinity, and now I have X, UK hat, and now I have UK hat, and now X multiplied on the right, or X star, I guess. Oh, there should be an X. I moved it to the right. So this is the same as this inner product, but now X is multiplied on the right. So this is just the same as X star op, which is in the right von Neumann algebra. So I can rewrite this now as this is the limit as n tends to infinity. And now we can take here. So now we're going to get phi of, I guess, oh wait, hold on. This should be AN. The X is still there. We moved the AN to this other star. Sorry about that. Where did AN go? Thank you, David. Yes, the AN should be there. So we move the AN to the other side, use the fact that ANs commute with B, A commutes with B, so ANs asymptotically commute with B, so we can move it to the other side, again, using this almost traciality property. And now we get this situation here, and now what can we do? Now we write AN as something in the right regular representation, so this is phi of now AN star op times X. And now we use this fact over here that I already wrote, that if we have something in the right von Neumann algebra, then the state doesn't see it. The state misses it. So now we can move it on the other side of the X. So this is the limit as n tends to infinity of phi of X AN star op. And now we can again go back to this formula and unwind it. And we see that this is, and then take a limit, and we see that this is phi of XA. So this is the situation we get. So we see that this, if we take X and the C-star algebra, and now A, anything, as long as it's in the relative commutant, so we use that crucially for this equality here. So then we can move A across the X when we apply phi. And now the point is that now we can use the fact that this C-star algebra, well, we have a state on it, so we can view the state as, we can take the GNS construction of the state. And so this is going to be some representation, which we can think of as a normal representation of the bidual. And sitting inside this normal representation, so we have this vector here, which gives us the state. So phi of x is equal to x c naught. C naught. And because phi restricts to the trace on the group, we see that this state here, this vector state, has some of the left regular representation in it. So specifically, we can take P, the support projection, of the left regular representation of the group in this representation. So the support projection of lambda in pi. So the fact that we have the trace says that there's some projection that gives us the left regular representation. So we just take the whole support of this. And now this is going to be some projection. So this P will be in the von Neumann algebra generated by the group. So in particular, it's in the double dual of this. So now we're almost done at this point. So now what do we have? Well, now we have this representation pi. We think of it as a representation on the bidual, a normal representation on the bidual. So this goes into B of H. And we have that, let me write this whole thing, let me write it as M to save notation. And so then what do we have? We have that, or rather pi of M, pi of this thing I'll call M. So then we have that M, when we cut down by this projection, this naturally contains the group von Neumann algebra sitting inside here. And we have that this state phi, we can think of this as a state on M and hence on PMP. This gives us state on PMP. So we have the phi gives a state on PMP, and such that, what do we know? We'd see that this formula holds here. So such that phi of AX is equal to phi of XA, and this is for all A in the relative commutant, and X, and now all of PMP, because it's a normal state here in the bidual. And now we see that the same proof I gave last time, which said that if you have a hypertrace, then you're injective. Well, the same proof I gave you shows that if you have a hypertrace here, so now therefore, what you get is that there exists a conditional expectation E from PMP down to the relative commutant here. But by hypothesis, the action was an amenable action. So this is a nuclear C-star algebra. So this is an injective von Neumann algebra. So this right here is injective, which means that there's a conditional expectation from B of H onto it. And so then composing these two conditional expectations, this therefore implies that the relative commutant is injective. And that finishes the proof. All right, so that's the proof. And I think the key takeaway is somehow the key thing which works is a string of inequalities that I've written here. So you use a few things. You use a sort of continuity, the fact that phi restricts to the trace on both the left and right group von Neumann algebras. So you can approximate things in the C-star algebra. Then you use this kind of smallness at infinity, or this particular boundary, to conclude that you can pass across from the left to the right when A is in the right regular representation. And then you use the fact that you almost commute with the UKs to pass across, to change the right regular representation, or the left regular to the right regular. So this is the outline of this proof. So what's something I want to remark about this proof, though? So the remark I should make is that so where do we use solidity? So we can do everything. If we wanted to just prove non-gamma, we could do all of this, and then we could take all A's in the whole group von Neumann algebra. So note, we can prove L gamma does not have the property gamma in the same way. Well, rather, if it's not injective. If it's not injective, then we show that it doesn't have property gamma in the same way. In that case, we can apply this for all A in the whole group von Neumann algebra because it asymptotically commutes with these UKs. But then we actually get a contradiction in an easier way, because we don't need to use the full force of this von Neumann algebra being injective, because all we need is that there's no central state on the whole group von Neumann algebra, and that we can check in an easier way. So in fact, what the proof shows is that if L gamma is, or has property gamma, so then there exists a state phi on B of L2 of gamma such that phi of x, I was using x before for the C-star algebra, so phi of AX is equal to phi of XA, and this is for all A in the group von Neumann algebra and X in this C-star algebra. So in particular, since we have this for all A, we can now put the group elements in there for A. So this then implies, and since we have this for all X, we can just take X to be in the commutative part. So we get, therefore, we get the phi of lambda t f lambda t minus f is equal to 0. And this is for f in the continuous functions here, and t and gamma. But then what does that mean? Well, if we strict this state phi to the continuous functions here, that gives us some probability measure. So this just says, i.e., that this space here, this completion, has a gamma invariant probability measure. Has a gamma invariant probability measure. And in particular, you get, therefore, your group is amenable, because if the actions on this is amenable, then you know that having an invariant probability measure means the group is amenable. We showed that last time. But in writing it this way, you notice that the fact that the action on this space is amenable, you only use at this very last step. So you get, from this, you get that, therefore, by exact plus property gamma implies that the group is amenable, implies the group is amenable. But in fact, yeah, so the by exactness you only use at this very last step to conclude that you have an invariant measure on an amenable action, then your group is amenable. But there are many situations where you can also just verify directly that there's no invariant measure here, even if it's not an amenable action. And so this naturally leads to a definition. So this is due to Boutonnet, Ioana, and myself. So we'll say that a group gamma is properly proximal if there is no gamma invariant probability measure on this space. Of course, the group gamma, the gamma acting on itself, there'll never be one if gamma is infinite, so or equivalently on the boundary. You can always restrict to the boundary because gamma acting on itself will never have an invariant probability measure. So this is the definition, and we see that the proof we just gave was, now I'll call it a proposition here, I'll just mention it, that if you gamma properly proximal, so this implies that L gamma does not have property gamma. But the nice thing about proper proximality is that, and the other thing you automatically get from this definition is that by exact and non-amenable immediately applies proper proximality. So let me maybe write that down. So the other, yeah, you see immediately also write it as a prop. So the gamma non-amenable and by exact implies that gamma is properly proximal. So at least there are a lot of examples of properly proximal groups, hyperbolic groups, for instance, or we saw explicitly the free groups. But the nice thing about proper proximality is it's actually much more robust. So there are many other examples. So let me give you another example. So first of all, yeah, so let me make a remark. So we can write this as a lemma. That, of course, this boundary of the group is too unwieldy to usually check in general. As I mentioned last time, this is usually, it's like the stone check compactification. So it's has some universal property, but we don't really have a very good description topologically of this boundary. So how you actually check that a group is properly proximal is you find some natural factor of this boundary that you can check this on. So specifically, by using the universal property, you can see the following. So gamma is properly proximal if and only if there exists an action of gamma by homeomorphisms on a compact Hausdorff space. Okay, compact Hausdorff. Without invariant measures. But we want this space to be like a factor space of the of this universal space, or really we just need that the probability space is a factor space of the universal space. So what we need is that, but there exists some probability measure on K, which necessarily won't be invariant, but we want it that it gives to a mapping from this smallness at infinity, this Owasawa boundary, into the space probability measures. And what that means is that it satisfies this property such that for all t and gamma, the limit as s tends to infinity of s eta minus st eta, so this is the weak star limit, should be 0. So I'll remind you that this property right here was exactly the defining property of this boundary that's small at infinity here. So the existence of such a measure means exactly, so here's the proof of this. The existence of such a measure means that we have a natural equivariant surjection from gamma union this smallness down to the space of probability measures, which just sends an element t and sends it to it t times eta. So this was exactly this condition here that I wrote, this formula was exactly the condition we needed to use this universal property. So if you have this condition, then you get this equivariant factor map. So if you have an invariant measure here, then you can push it down to an invariant measure here, but then you can take the Chebyshev center to get an invariant measure on K. So that's how you prove one direction. The other direction's obvious because this boundary satisfies this. Okay, so that's how you prove this lemma. And here's where you actually check if a group is properly proximal, is you need to find some natural action which does not have invariant measures, but does have some measure of this type. So let me go ahead and give you an example of where this happens. I want to copy this over. So here is an example. It's an example / definition. So a group gamma is a convergence group if there is an action by gamma onto, again, a compact Hausdorff space without invariant measures. And such that we have this sort of north-south dynamics. We have north-south dynamics. So what do I mean by that? That means that, i.e., if we take any sequence, Tn and gamma, and Tn go to infinity, so we can't concentrate on a finite set, for instance. So we escape every finite set. So then there is a subsequence, Tnk, and there's also 2 points, A and B, a source and a sink in K, or the south and north, such that for any neighborhoods A of A and B of B, we have that outside of this neighborhood of A, so if we apply Tnk to the complement of A, then it'll eventually be contained in B, or K large. So that's the definition. Let me draw a picture because you can probably see more from the picture than you can from the definition. So the picture is, we have something like this, and I'm drawing a circle for a reason I'll mention in a moment. So you have some sequence of your groups, and you have some A over here, and you have some B over here. And if you take, so any neighborhood of A, so some small neighborhood of A, and any neighborhood of B, something like here, then applying TK, you move this entirety of this neighborhood, everything outside of this neighborhood, you move into B. So it's like you collapse the entire space to B. So the canonical example of this situation is if you look at, in fact, this definition, so this is not my definition, this is studied by group theorists for the 20 or 30 years. And the example that they're trying to generalize in this is if you look at SL2R, or any discrete subgroup of SL2R, acting on, say, the circle by fractional linear transformations. Then you exactly have this kind of stretching and shrinking property. So your translations are these rotations, and then you have the stretching or shrinking. And so this is exactly the phenomenon, this sort of dynamical phenomenon has been well studied in this case, and there are many generalizations to this situation. So other examples are, for instance, gamma hyperbolic, and gamma acting on its Gromov boundary. You also have even gamma relatively hyperbolic. So then there's a natural boundary there. And a particular example of that is, for instance, gamma being a free product of gamma 1 and gamma 2, acting on the boundary of the Basser tree is acting. So for here, you want that, say, gamma 1 has at least 2 elements and gamma 2 has at least 3 elements to get that there's no invariant measure on the boundary of the Basser tree. So these are all examples of this sort of generalization. But I claim that this exactly fits in with this notion of proper proximality. So the claim, so write it as a proposition. So convergence groups are properly proximal. And the proof of this, well, we have the space on which we act on that comes from the definition of a convergence group. So the only thing we need to do is we need to find this measure. If I go back for a moment, we need to find this measure that satisfies this formula. So we need to just show that if you have a convergence group, then there's some measure which satisfies this formula. But the nice thing about convergence groups is we can take eta to be any measure without atoms. And if you take eta to be any measure without atoms, and you think about what happens in this north-south dynamics, what it says is that if you take if you take this sequence and there's a subsequence such that when you take the push forward of any measure where you take every set outside of any neighborhood of A, collapse it into a neighborhood of B, what that's exactly saying is that you take any measure without atoms, so specifically we just need that there's no atom at A, then it collapses everything to the Dirac function at B. So that's a remark here. So that's if eta diffuse. That's a simple consequence of the fact that it's a convergence action. So now the B that you send it to may depend on the sequence you take, but there's always some point where it collapses to a direct function. In particular, you notice that this doesn't depend on the measure eta. The only thing that it depended on was that eta was diffuse. So therefore, if you take eta and then you translate eta by some group action, then both of these get sent to the same Dirac measure, and in particular, their difference gets sent to 0 in the weak star topology. So that's the sketch of the proof that convergence groups are properly proximal. So this gives a nice source of example. The other source of example, and this is what I'll do next time, I don't have time to finish the proof today, is that in fact, so this I actually call a theorem because this takes some work, is that if gamma is a lattice in a non-compact semi-simple Lie group, so then gamma is properly proximal. So for example, we have gamma, a group like SL3Z or SLNZ for any n. So this is maybe what I mean by the robustness of proper proximality, is that, by exactness was really kind of a rank 1 for phenomenon. It didn't allow any sort of commutation or anything like this. But proper proximality is much more general in the sense that it does allow some sort of commutativity. Now you don't get solidity results, of course, from proper proximality, but many of the by exactness results you do get in this situation. And I'll mention some of those also in my next lecture. I should also remark that proper proximality is closed under taking direct products. So for instance, a free group direct product to free group, this is definitely not by exact, but it is properly proximal still. And then I mentioned that property gamma, if your group von Neumann algebra is property gamma, then you're not properly proximal. And in fact, more or less the same proof, if you track it down, in fact shows that if gamma is not, or if gamma is interamenable, so then gamma is not properly proximal. So this is one obstruction to being properly proximal, is if you're interamenable. And for a little while, this was the only obstruction that we knew about. But there's one more. Let me write out the example here. So if you look at SL3, you take a finite field with P elements, P is some prime, and then you join some indeterminate. So this gives you a ring, and you look at the group, SL3 of this group, and now this acts on FP, and now you can throw in two indeterminates like this, cubes. So this is an abelian vector space, and your group acts on this abelian vector space, and so this gives us a group, a natural group, and this is not properly proximal. And is not interamenable. And I'll discuss the proof of this fact also in my next lecture. So proper proximality, it's still a bit of a mystery. There are many examples where it is. Here are some where it's not, but it's not exactly still clear. Here are some open problems. And that is if you have acylindrically hyperbolic groups, so that's open. I want to give myself just a little bit more room here. So that's an open problem. Groups with positive first L2 Betty number, that's open, or even if they have some positive first L2 Betty number. So we don't know if these are properly proximal in general. So out of Fn, so that's an example of an acylindrically hyperbolic group, which we don't know specifically. So these are all things we don't know. ICC property T groups. We don't know if they're properly proximal in general. So these are all examples. Additional examples I should mention are hierarchically hyperbolic groups. So this includes mapping class groups. So this was a result last year. I wrote down the attribution here in my notes. Somewhere. There it is. So this is due to Horbez, Wang, and Lacroix. And then I'll also mention many amalgamated free products. A little bit more room. And this is a result which was spoken on earlier at this conference by Ding and Kunawalkam Eliabali. Hopefully I said that well enough, Sri. I've been practicing. All right, so now I think I'll go ahead and stop here and I'll discuss more of these in my last lecture tomorrow.